Let us work out a few examples to illustrate the idea of convolution. Okay, so number one, let us take a general function, let me call it by x of t, and try to convolve with the delta of t. Then let us see what is the answer, okay, and see what happens. So I am taking some general function, and this is a impulse function. So general function is convolved with an impulse function. So you have two time functions, right? See, this is the input del of t, and no, for the time being let us forget about this. So let us say y of t is equal to x of t convolved with the del of t. Now these two are time functions and the result also time function, right? Therefore, since the final convolution is a function of time, the output is a function of time, you are doing some integration. So this is x of tau del of t minus tau. So the result is d tau y of tau minus infinity to plus infinity. So see, this is t, I am sorry, this is t. So the final result is also in terms of time. Independent variable is time. Therefore, while doing the integration, we use some dummy variable. Otherwise, we will be in trouble. Okay, so that's why we use this is a dummy variable. This tau is a dummy variable, and here also tau is a dummy variable. It would be advisable for us to involve another variable, okay, which gets integrated in the process. So that's why instead of taking x of t, we are taking x of tau, because final answer I need in the form of time y of t like this. Therefore, introduce tau here, dummy variable. Similarly, the del of t also becomes del of tau, that also dummy variable. Okay, so let me take some function like this, arbitrary function, let me call x of t. Now I will change the variable, same function like this, but now it is going to be x of tau, and here the time x axis is time, and here x axis representing tau, both are time only. Similarly, if we have a delta function like this, let us say t, and this is del of t. Now I am going to represent this guy as like this. Okay, this is del of tau, and here it is time axis tau. So now this is delta tau. Now one can ask a question, what is del of minus tau, because the second step is folding, first step is over. What is the first step? If you recall, x of t to x of tau, and h of t to h of tau, that's what we discussed in the last class. Here instead of h of tau, I have del of t, and this del of t becomes del of tau. So first step is over. What is the second step? Second step is folding, that is del of minus tau. We know that delta t is an even function. So if it is an even function, then it looks again the same. Therefore, del of tau is the same as del of tau. Del of minus tau is the same as delta minus tau. So let us say this is del of minus tau, because if you look at a delta function, it is very small thin, and this is going to be 0 minus, and this is going to be 0 plus, and the center point is 0, and the area under this curve is 1. this is your del of t, sorry, let us say del of tau. So, even if you flip over about the y axis, then it will not change. Okay. So, if you fold it, it becomes the same thing. Now, what do we want to do? What is the third step? Third step is shifting, right? Like del of minus tau is going to be del of t minus tau, right? So, now again by the symmetry property I can write this as same as t minus tau. Why? Because it is an even function. So, because of the even function, that is equal, both are equal. Now, if you take this minus inside, then del of minus t plus tau. So, if you want to now, then the next step is multiply, I mean your x of tau and the shifted version, this guy, what is that guy? Del of minus t plus tau, multiply these two things. So, product. So, if you want to calculate the product or the convolution at a value t, you shift it by an amount, this small t. Okay. So, one second, I have done some small, this is correct only, but still we can write in another form also. So, therefore, you can take either this one or you can take this one also, no problem, del of t minus tau, whichever is like you can take it. Let us take this one. Even if you take this, you will get the answer, no problem, this is also perfectly right, correct. So, let me take this one. Either take this one or this one, does not matter, this one, any one you can take it. So, let me stick on with the del of t minus tau. So, del of t, it becomes del of tau, then again change of independent variable, then you shift by time instant, fold it. So, del of minus tau, then delay it by t seconds. So, del of t minus tau, this is the whole process. Now, you take that del of t minus tau and multiply with the x of tau. So, it is a product. Okay. Now, we know that your del of minus tau is like this. If t is less than 0, then your pulse looks like this, maybe somewhere it looks. This is del of t minus tau when t is less than 0. Or else I can remove this guy. Now, it may look somewhere else. This is this point is 0 and this point is 0, tau axis, this also tau axis, this also tau axis. Now, this point is t, let us say del of t minus tau if t is greater than 0. For example, let us say t is equal to minus 1 second. Then what happens? Then originally this is your del of minus tau, let us say tau axis, then it is delayed by 1 second. Let us say this point is 1 second, minus 1 second, this is 0, this is plus 1 second. So, this is del of 1 minus 1 minus tau, because we assumed t is equal to minus 1 second. If you assume t is equal to minus 2 seconds, then your signal will be 0, this is 1 and this is 2, like this, minus del of minus 2 minus tau, this is tau. Okay, so here we assumed t is equal to minus 2. So when t is less than 0, the pulse is shifted to the left. When t less than 0, the pulse is the same concept, again and again I am repeating, the pulse is shifted to the left. Similarly, if t is greater than 0, let us say t is equal to 1 seconds, then this is your, let us say, del of minus tau. Again, del of tau and del of minus tau, one and the same. This is my tau time axis. Now let us say t is equal to 1 second. In this case, what happens? 0, 1, 2 like this, 0, 1 second. So your pulse locates here. This is del of 1 minus tau. And again, this is tau axis. Okay, so whenever t is greater than 0, let us say 3 seconds, then this point is 0, 1, 2, 3. Therefore, your impulse is located at t minus tau. That's it. Okay, so that is our basics. So you have x of t like this. Let me call x of tau. This is tau. Then your shifted impulse will be somewhere sitting like let us say here, del of t minus tau, where t is greater than 0. Now you multiply let us say the second one, and let us say this is the first one, 1 and 2. Okay, so this point is time t, and here also this point is t, and corresponding to this point the value of the function is x of t. For example, let us say 1, at this point you substitute tau equal to 1 in the function x of tau. So what is this value? That value is going to be x of 1, right? Similarly, instead of 1 I have t here. Okay, if you substitute t in the function, then this point is going to be x of t. Now it is a constant, by the way. Okay, please remember, it is not a function now, it is no more a function. Once you substitute tau is equal to t, then x of tau becomes a constant. So please remember, don't get confused. See, x of tau is a function. Okay, it has values, function of t, but the moment if you substitute t, but if the moment you substitute tau is equal to t in the function, then you will get x of t. Now x of t is a value. Okay, it is a number. Okay, it is not like a function. Okay, so multiply this and that, so you will get x of tau del of t minus tau. So this one is, how do you get? You first fold the signal x of del of tau to del of minus tau, and from there you shift by t samples x of t minus tau, and then multiply this del of t minus tau with the x of tau. If you multiply these two, what you get is, again let me write down, x of tau del of t minus tau is equal to x of t, the same function, delta function, del of t minus tau. Recall this property from your impulse function from the previous lectures. Okay, and this is a constant, as far as the integration is concerned, because finally what we want, your y of t is equal to integral of x of tau del of t minus tau d tau, right. So integration is minus infinity to plus infinity. Now this one is going to be x of t from this x of t del of t minus tau d tau. What is x of t now? It is a constant as far as tau is concerned. You are substituting only one value now. So bring out of the integration. So x of t times integral of del of t minus tau d tau. Now what is this? This is the area of unit impulse sitting at where tau is equal to t. So what is the area? As per the definition, it is equal to 1, the whole integration. So therefore x of t, your y of t is x of t. Okay, so the integration gives the area of f of x of t times del of t minus tau, which is again x of t itself. So the result is that x of t convolved with del of t is x of t itself. So you take x of t convolved with the del of t, the result is again x of t. So this is a very, very important result, I should remember. Okay, so this is a very, very interesting result, that the del of t delta function, when it convolves with any time function x of t, yields the same function identically without any change. Okay. Of course, in practice you may not have delta function exactly like when t equals 0, but if you have like narrow slit like this delta function, this point is 0 minus and this point is 0 plus, it is a narrow slit. Okay. For example, instead of delta function, suppose you are having a small slit like this, you do the same convolution whatever we did till now, then you get an output which is closely resembling to x of t itself. If you do the convolution with x of t, then you will get closely x of t, almost same. That's why I put approximation symbol here. Okay. Now let us take the second example. Let us see what happens when a step function u of t is convolved with the another step function u of t, unit step function. Okay, so this is what we want to find out now. Let us say y of t is equal to u of t convolved with the u of t. Now what is, as per the definition, convolution integral definition, it is minus infinity to plus infinity u of tau u of t minus tau d tau. What is the first step? Change the variable of integration, because finally the output also function of time, and here also if you put a time now, then you will be in trouble. So that is why we are changing t to tau as a dummy variable. Once you do the integration, the dummy variable will disappear. That is the reason we are doing this kind of thing. So u of t becomes now u of tau, and another u of t also becomes u of tau. You take any one function. Let me take the second guy. So this u of tau, this the first step is over. Second step, what you need to do? You fold it up. You take this guy and fold u of minus tau. If you plot it, this is u of t time function, then change the variable u of tau like this, this is tau, then u of minus tau looks like this. Okay. Again this is tau and this function is u of minus tau. Okay. So second step is folding. What is the third step? Third step is shifting. either a shift to the left or to the right and then multiply. Now here we can do two types of shifting, one is to the left and another one is to the right. The first one is, let's say t is greater than 0. When t is greater than 0, that means you are shifting the function to the right like this. This is u of t minus tau and this is t and this is tau. Here this t is greater than 0. That means, for example, let's say t is equal to 3 seconds, then 0, 1, 2, 3, then your impulse will come like this. So this is u of 3 minus t and this 3 is a positive number, right. So let us take the positive cases for the time being and then we will consider the second case. Maybe I will draw the figure here. When t is less than 0, for example, t is equal to minus 1 or t equals minus 2 or whatever it is, then in that case your function looks like this. This is t again, but here this t is negative. So u of, again same notation, but here this is negative. For example, if t takes a negative value, that is minus 1, then this is 0, this is minus 1, your function looks like this. Okay, so this is u of minus 1 minus tau, like that. So let us take then third step is over. What is the fourth step? Multiply. And one function is u of tau and the second function is u of t minus tau. Here we are considering t greater than 0. Two times you consider, two types of multiplication that we are going to do here. The first one is t greater than 0 and the second one is u of t minus tau, but now t is less than 0. Take this guy first. So this is u of tau and when t greater than 0, this is your function like this. The function comes like this. Let's say this is t tau and this is u of t minus tau, where t is greater than tau. Sorry, t is greater than 0, I am sorry, t is greater than 0. Therefore, it is shifted to the right. Now multiply these two guys. Okay, what is the overlapping area? If you look at, term by term you multiply. See, in this region it is 0, the function is 0. Okay, now we extend this like this. Therefore, in this region it is non-zero, this areas, right. If you multiply these two, what will you get? So you will get a 0 area, 0 from t equal to, sorry, when tau equals t onwards, this is a tau axis by the way, this area is, product is 0, product of u of tau with the u of t minus tau is 0. Now what about this area? Let me choose some other color, some nice color, this area. Now multiply the function, it is not area, let me, this is 1, magnitude is 1 and this also 1. So 1 times 1, again 1 square, right. Therefore, you will get a 1 only, this is 1. Okay. So this is the area, sorry, I am sorry. So this is the one you get after the multiplication. So this is u of tau, u of t minus tau. Okay, maybe I will write down very clearly. This is u of tau, u of t minus tau, where t is greater than 0. Fine. Now let us look at the third case, I mean left hand side. Let me choose this color. Then if you look at here, the value is 0, okay, and but here it is 1. So 1 times 0 again 0. Here the value is 0 of u of tau has 0 value, and this guy has 1. 1 times 0 0, therefore this becomes 0. 0. So this is what I get. Now as per the thing, it is integration of minus infinity to plus infinity, u of tau, u of t minus tau, d tau. Now you can split the integration into 3 integrations. You start from minus infinity, come up to 0, and 0 to t, and then t to plus infinity. So there are 3 integrations in this. So minus infinity to 0, u of tau, u of t minus tau, d tau, plus 0 to t, u of tau, u of t minus tau, d tau, plus t to infinity, u of tau, u of t minus tau, d tau, right. Now what is this is equal to, in this integral it is 0. Therefore integral of minus infinity to 0, 0 times d tau, plus 0 to t, what is this? This is equal to this one. What is that value? It is a constant 1, 1 times d tau, and this one is equal to this value. So that is again 0. This is 0, right? So t to infinity 0 times d tau. Therefore the first one is 0, plus second one is t, and sorry, tau, the limit is 0 to t, plus third one is 0, third integration. So you will get t, okay. Therefore your output y of t is equal to t for t greater than 0. Fine. So this is one thing, we got it now. Therefore the area under this curve is t units. The resultant of u of t convolved with the u of t is going to be t for t is positive t. So we can say this is for t greater than 0, right? Because we shifted in the forward direction to the right. Forward direction means to the right. Now let us imagine what happens when you shift to the reverse direction, I mean to the left hand side. So second case. So this one is the first case. Where did I do that? Yeah, this is the first case. Now let us take second case, when t less than 0. The second case, u of tau, u of t minus tau, where t is less than 0. In this case, this is your u of tau, right? Then this is your u of t minus tau when t is less than 0. This is somewhere this t is. Now there is no overlapping area if you look at these two guys. Okay, for negative t, you shift in the negative direction. You shift u of minus tau in the negative direction. Okay. So if you shift in the negative direction, then you don't have any overlap. So this is the curve which looks like this when you shift in the negative direction. So when you make the product u of tau times u of t minus tau, then what happens? See, here I have non-zero area, right, up to t, but here I have 0. Therefore, product of this guy and that guy become 0. Let me change to other color. And here again it is 0, and here also again it is 0. Product of these two guys will give 0. And then here it is 1, but here it is 0. So if you take product of these two, then again this is 1 and this is 0. 1 and 0 becomes again 0. Therefore, for any region from minus infinity to plus infinity, u of tau times u of t minus tau times d tau is equal to 0. Therefore, your y of t is equal to 0. Okay, the product is 0. That is, the product of u of tau times u of t minus tau is going to be 0 identically. Therefore, the area is going to be 0 and the convolution product is 0. So, finally, your result is y of t is equal to u of t convolved with u of t, which is equal to t for t greater than 0 and 0 for t less than 0. So, this is something resembles with something else. Don't you see that this is a definition of your ramp signal r of t. So, the convolution product of u of t times u of t is described by r of t. So, this is a ramp function. So, how do you describe the ramp function? It is 0 up to time t is equal to 0, and then it increases the slope of 1. So, this is t. So, the idea of convolution is relatively seen in simple cases by plotting these graphs in this manner. So, u of t convolved with u of t is equal to, simply I can write r of t. So, important result. So, let me summarize again the keywords. First is change of independent variables. Independent variable t to tau, because again the result is going to be in terms of function t. That is why we are introducing some dummy variables in the integration. And the second step is fold operation. And third step is shifting to the left and shifting to the right and so on. And the fourth step is multiply the two functions, and the fifth step is carry out the integration. That's all. Very simple operations, but you should do it very carefully. So, integrating means what? Finding the area of the product. Find out the area under the curve, under the multiplication of two functions. One is the function as it is, and another function is folding and shifting. For simple geometrics, the area to the curve can be easily found out without doing integration also. No need to do the integration, simply you can find out. Okay, so you can picture what the final result is using this concept. Let me take one more example. Third example. So, given it is fairly mechanical steps. It is 2 times e to the minus t minus e to the minus t multiplied by u of t. So, the condition is initially relaxed linear time invariant system. Relaxed linear time invariant system. Generally, people will write LTI system. So, in short form, it is very famous abbreviation, LTI system. Okay. Now, find the response to first option is u of t. Input is u of t and find the response. And the second one is input is minus 3t and u of t. So you have a system h of t and the input is u of t and find out the output. Now when the u of t is the input, then output is denoted by, recall it is a of t, it is denoted by a of t or s of t. Okay, you can use a of t or s of t, but let us use a of t. And this is our first part. Second part is you take the same system h of t and now the input is e to the minus 3t times u of t. Now the output is y of t. Let us say this is arbitrary input. Now we need to find out. This is a question in front of us now. Okay, so we are asked to find out using this impulse response. Okay, the response to two arbitrary inputs. The first one is u of t and the second input is e to the minus 3t times u of t. Okay, so if you apply u of t, then it gives rise to a of t, or you can use a notation s of t also, no problem, but let us use a of t output. Therefore, a of t is equal to u of t convolved with the response h of t. Okay, if u of t gives rise to a response a of t, then a of t can be found out by convolving u of t with the h of t. Now look at the question carefully. They said initially relaxed time invariant system. What do we mean by that? There is no initial condition. That means this is a causal system. H of t is equal to 0 for t greater than 0. T less than 0. T less than 0. Before you apply the input, there is no output. Okay, that's what we mean. So if h of t is equal to 0 for t less than 0, then because of this causality and the signal also causal signal, because of these two things, if you recall from your previous lecture, if the system is causal, if the signal is causal, then the limit is from 0 to infinity x of tau. Maybe I'll write down here. Two conditions. One is causal input signal. In that case, your LTI system becomes y of t is equal to 0 to infinity x of tau h of t minus tau d tau. That's what we mean by this. Because your x of t starts at if causal signal, we know the definition. Causal input signal is a signal where causal input signal where x of tau is equal to 0 for tau less than 0. Similarly, because of that, the lower minus infinity will go away. Now causal system is a one where h of t or h of tau is equal to 0 for t less than 0. Therefore, this is for causal input signal, then causal input and causal system. In that case, both are there. Then interval of 0 to t x of tau h of t minus tau d tau. Please recall this one. I have discussed in the last lecture. Okay. Now the h of t is equal to e to 2 times e to the minus t minus e to the t times u of t. See, this is h of t is equal to 0 for t less than 0. You can substitute and you can verify. If you substitute t is equal to minus 1, then this function becomes 0. The whole thing will become 0. So this is the causal system. The given system is causal and initially relaxed. That's what we mean by. And u of t. What is x of t? X of t. The input is u of t. Again, this is causal signal. Right. So the given system is a causal system. The impulse response is 0 for negative values of time, and the input is also causal. Therefore, we can straight away say that the integration limit is 0 to t, and this is equal to your a of t. So a of t is equal to u of tau h of t minus tau d tau. So here no need to draw the picture and all, straight away you can substitute the expression here. We have the expression. So 0 to t in the interval 0 to t, when tau takes positive values, then this is going to be 1. Therefore, straight away I can write h of t minus tau d tau. That value is 1, right? Unit step function. Okay, that is going to be 1 anyway. Therefore, we can disregard u of tau. Okay, if we disregard u of tau, then it becomes h of t minus tau d tau, and the limit is 0 to 1. Now we know h of t, so we substitute, simply replace t by t minus tau, then it is 2 times e to the minus, t is replaced by t minus tau minus t minus tau, then multiplied by u of t minus tau d tau. Again, this is also equals 1 when tau is greater than, they should actually, the argument should be positive. Hold on one second, t minus tau should be positive. Therefore, t should be greater than tau, or tau is as long as less than t, then no problem. So that is equal to 1. So 0 to t, you rearrange this, 2 times e to the minus t times e to the plus tau, right, minus e to the minus t times e to the plus tau and d tau. Okay, so and I think I have done a mistake. What is the input? I think I copied the question wrongly from the textbook. It is minus 2t. So wherever you find that, you replace by minus 2t. Minus 2t, then here also it becomes minus 2t. I copied the question wrongly, nothing else. Then it becomes minus 2t and plus 2 tau. Okay, that's all. So you split into two integrations. So 2 times e to the minus 2t, integral of e to the 2 tau d tau, and this is t, minus e to the minus tau 0 to t e to the tau d tau. So again do the integration, 2 times e to the minus 2t, and this is e to the 2 tau divided by 2, and the limit is 0 to t minus e to the minus t e to the tau 0 to t, and this 2 and that 2 will get cancelled. So e to the minus 2t times e to the 2t minus e to the 0 minus e to the minus t e to the t minus 1. So this is going to be if you multiply this in this guy and that guy, then it becomes e to the 0, that is 1 minus e to the minus 2t. Okay. Minus, here minus, it becomes, if you multiply inside, it becomes 1 e to the 0, then minus e to the minus t. You take the minus sign inside, then it becomes plus 1 minus e to the minus 2t minus 1 plus e to the minus t. So e to the minus t, 1 and 1 get cancelled, minus e to the minus 2t, and this one is valid only for t greater than 0. Therefore, your output a of t is equal to e to the minus t minus e to the minus 2t for t greater than 0. Or you can write a of t is equal to e to the minus t minus e to the minus 2t multiply by u of t. That's all. Because we consider only for positive values of time, no, 0 to t, that is why where t is greater than 0. Now let us go to the second case. Now the input x of n is not u of tau, it is e to the minus 3t and u of t. This is not x of n, it is x of t. Fine. Now same process. What is your y of, again this is causal signal and a causal system. This is causal input signal. And h of t is causal, therefore it is causal system's impulse response. Therefore integral of 0 to t x of tau h of t minus tau d tau. So 0 to t x of tau is e to the minus 3 tau u of tau multiplied by e to the minus t minus tau. So it is going to be 2 times e to the minus 2 times t minus tau minus e to the minus t minus tau multiplied by d tau. Now split into two integrations. So 2 times e to the 2t minus 2t you can pull out from the integration, then 0 to t, if you rearrange it becomes e to the minus tau d tau. This u of tau is going to be 1, so you can leave it. And here also you will have one function, that is u of t minus tau d tau. This also is equal to 1 for tau less than t. Okay, minus e to the minus t 0 to t e to the minus 2 tau d tau. So do the integration. I am sorry, this is minus 3 tau and here plus 2 tau. Okay. Okay, correct, this is correct only. Okay, so 2 times e to the minus 2t, what will happen now? Okay, let us work on it. So this is e to the minus tau divided by minus 1 and the limit is 0 to t minus e to the minus t. This is e to the minus 2 tau divided by minus 2, right? So 0 to t, then this is 2 times e to the minus 2t, within a bracket you will have e to the minus t times in the denominator you have minus 1, this is 1. minus e to the minus t, then e to the minus 2t, then minus 1 divided by minus 2. If you rearrange all the terms, then finally you will end up with them. I am writing it's a matter of algebraic simplification, that's all. Minus 3 over 2 e to the minus 3t plus 2 times e to the minus 2t minus e to the minus t by 2. So, this is the output y of t. And of course, this is valid for t greater than 0. Notice that in this particular example, we have found the complete solution. So, this is complete solution. Whenever you find a solution for a system, you have two types of solution. One is complementary and another one is particular solution. If you solve a differential equation, you will get a complementary and particular solution. Okay, after all, the input is e to the minus 3t. This is the input. The same input is appeared in the output. And this one is called a particular integral, and this one is called a complementary solution. Okay, and this one is called a forced response or particular integral. If you recall from your school mathematics, when you try to solve the differential equations, you will get two solutions. One is when you make input x of t equal to 0 and you will find the solution for y of t, that is called a complementary function. Okay, that complementary function is called a natural response, the response given by the system without any input. And when you give the input, then that is called a particular integral. Anyway, we will discuss these things in detail a little later. Okay, therefore, the forced response will have only this particular e to the minus 3t. Okay, and this 3t, where 3 is a complex frequency, s is equal to minus 3. This is the complex frequency, right? And then the second part, this part is called a natural response. Which contains a response when there is no particular input, that is called a natural response. In mathematical term, we call it a complementary function. Recall, if you have d square y of t by dt plus 3 times dy of t by dt plus y of t is equal to, say, some 2 times x of t, then how do you find the solution for this? You replace this is by d square plus 3d plus 1, let me put 2 here, plus 2 is equal to 0. So, m square plus 3m plus 2 is equal to 0. So, you will write m plus 1 times m plus 2 is equal to 0, right? Now, m is equal to minus 1 and m is equal to minus 2, and you write the solution for this e to the power of m1x, let us say m1 and m2, m1x. So, m1 is minus 1 minus x plus b times e to the minus 2x, and so on. So, this is called a complementary solution. In the mathematicians will call complementary solution, but here we call natural response. The same response is occurring here, this one, which is highlighted in the pink color, sorry, violet color or whatever it is. And this is natural response, and this is your forced response, particular integral. So, in the particular integral, what you do, you will not make this guy to 0, you will take the 2 times x of t also, and then you will solve it. So, whatever you are studying in the mathematics, that has so much useful in signals and systems also. Therefore, the impulse response here, whatever the frequencies are present at the input, the same frequencies appearing in the output also. So, the forced response for x of t is equal to e to the minus 3t will also have this e to the minus 3t. So, you can recognize this e to the minus 3t multiplied by minus 3 by 2 to be a forced response or particular integral. So, this is the, and rest of the things, this one is the natural response or complementary solution. Okay. So, let me stop at this point.